This video is about Pierre Duhem's Underdetermination thesis. Duhem was a late 19th and early 20th century physicist, historian, and philosopher of science. His most influential work among philosophers is his book The Aim and Structure of Physical Theory, which was originally published in French in 1906 and whose English translation appeared only in 1954. Among philosophers, he's remembered for his Duhem thesis, which states that physical hypotheses are never tested in isolation. He also defended a very closely related view that states that data underdetermines the theory that explains it or predicts it. So let's have a closer look at what Duhem says in The Aim and Structure of Physical Theory. Duhem was very interested in the logic of experiments of testing. He distinguished experiments of testing from experiments of application by focusing on the difference between applying a scientific theory toward a specific outcome as opposed to testing a scientific theory. And he was really interested in how scientific theory testing worked. What is the logic behind a test for a scientific theory? For Duhem, it seems as if what's going on in an experiment of testing is that you have some theory T that implies some empirical evidence E. And if you don't see that empirical outcome, then you simply say that the theory must be wrong. So this looks like a simple deductive argument pattern that we call modus tollens that seems to have the same sort of certainty as a reductio ad absurdum in mathematics. However, for Duhem, this is not how experiments of testing really work. Instead, what's going on in an experiment of testing is a bit more subtle. For Duhem, it's not just the single scientific theory itself that implies some empirical outcome. Instead, the expected empirical outcome is the result of assuming not just a scientific theory, but a whole host of other auxiliary hypotheses, H1, H2, H3, and so on. So that if we don't see the expected empirical outcome, then the most that we can conclude is that something went wrong. Something is false in that big conjunction that is T and H1 and H2 and H3 and so on, but we don't know which one or which ones of those hypotheses and theories might be wrong and might be what's leading the experimental outcome not to be observed. So this means that experimental testing or experiments of testing, when we're testing a scientific theory, have a logic that's much more subtle, because knowing that something is wrong is not nearly as definitive as showing that the theory is false. So here's how Duhem puts it. He says, the only thing the experiment teaches us when it has a negative outcome is that among the propositions used to predict the phenomenon and to establish whether it would be produced, there's at least one error. But where this error lies is just what it does not tell us. And of course, working scientists know this about science very, very well. If you're setting up an experiment to test a hypothesis and the experiment does not reveal the expected empirical outcome, you don't immediately run out and think you're going to publish a paper saying that the hypothesis is false. First, there's a lot of other things that you have to check that are precisely the kinds of auxiliary hypotheses that govern, for example, the way your instruments work, that you want to be certain are not the problem that led to the empirical outcome not being observed. So Duhem concludes, the physicist can never subject an isolated hypothesis to experimental test, but only a whole group of hypotheses. This is a really important point. It means that although it might seem as if a scientific experiment is only testing one hypothesis, it's actually testing a whole cluster of hypotheses. He continues, when an experiment is in disagreement with his predictions, what he learns is that at least one of the hypotheses constituting this group is unacceptable and not to be modified. But the experiment does not designate which one should be changed. Again, because in the logic of an experiment of testing, there's a conjunction on the left side of the implication arrow, and when the experimental outcome isn't borne out, what we can validly infer is the negation of that long conjunction that's in the parentheses in the conclusion. This is really to start emphasizing a different way of thinking about science. And to really bring this to the foreground, I think it's worthwhile to look at how Duhem compares physical science to an organism. It's an interesting comparison because it can stand in sharp contrast to the way that, for example, the logical positivists thought about science, and perhaps even today, the way some scientists and the general public think about science. Duhem states, physical science is a system that must be taken as a whole. It is an organism in which one part cannot be made to function except when the parts that are most remote from it are called into play, some more so than others, but all to some degree. This is a really interesting thing to think about, this comparison that Duhem is making here, the idea being roughly this. When we think of physical science in general, whatever that means, whether it means all of physics or physics and chemistry or whatever, if something doesn't match a prediction, it's like the whole organism is unwell. And scientists then turn into a sort of diagnostic mode where they try to problem shoot what might be wrong. But that process is not as well defined as it might sound. So here's how Duhem explains it. If something goes wrong, if some discomfort is felt in the functioning of the organism, the physicist will have to ferret out through its effect on the entire system which organ needs to be remedied or modified without the possibility of isolating this organ and examining it apart. Again, it's a pretty powerful metaphor. The idea that physics, or maybe all of physical science, is an interconnected system of hypotheses where we cannot ever test one in isolation from the rest. We can only test clusters of hypotheses and compare them to other clusters and do our best to narrow down what might be the problem if part of our empirical outcomes, if some of our empirical outcomes are not coming out as we expect them. So think about that as you go on to read Quine, because what Quine is going to do now is he's going to take this idea that we never test a single hypothesis in isolation and generalize it to all human knowledge. For Quine, it's not just in physics or in physical science that we can never test a single statement in isolation. That's true in general for all human knowledge. So I hope you enjoy reading the rest of Duhem, and that'll give you a really good solid footing for heading on and reading about Quine's web of beliefs.